Hello everyone, this is the second linear algebra inner lecture. In continuation of previous on-site lecture, I will explain on the Gaussian elimination with two examples. Example 3 and 4. Chapter is 7.3. As I said before, the augmented matrix is composed of coefficient matrix like this and right hand side of a linear system. The problem is solve the following linear systems of three equations in four unknowns. Three equations. There are mismatch between number of equations and number of unknown. So how can we solve this problem? Let's go together. These are linear system equations, including variables and left-hand side and right-hand side of constants. This can be converted row equivalently using augmented matrix form. The coefficient matrix is here and right hand side is here. To solve this problem, as a first step, we have to eliminate x1. Firstly, to solve this problem, we can select pivot and with this pivot variable pivot term and elimination term like this. To eliminate x1 from the second and third equation, we can add minus 0.3 divided by 3 equal to minus 0.2 times the first equation to the second equation. We add this first equation and second equation by multiplying minus 0.2. Okay. And for third equation, minus 1.2 here and 3.0 here. We can divide here this digit to digit, this digit, and makes minus 0.4 times first equation to the second and third equation, like this. Row 2 plus minus 0.2 multiply row 1. Row 3 plus minus 0.4 multiply row 1. This gives the following another augmented matrix like this, in which the pivot of next step is circled. Okay. Here can be the next pivot. Here can be the next variable to be eliminated. As a second step, elimination of x2. From this augmented matrix, we can derive another augmented matrix which is eliminated, which does not include x2 variable. To eliminate x2, the pivot can be 1.1 minus 1.1 divided by 1.1 and multiply minus 1 is equal to 1. 1 times the second equation to the third equation. This makes here like this all 0. Coefficients are 0 and right hand side is 0. Is equal to this equation. Okay. Finally, as a third step, back substitution have to be conducted. From the second equation, we can see here second equation to make in forms of x2. x2 is equal to minus x3 plus 4x4 here. x2 is equal to 1.1 minus 1.1. Oh, sorry. 1.1 x3 plus 4.4 x4 divided by 1.1. So x2 is equal to 1 minus 1x3 plus 4x4, like this. And for third equation, here x2 can be substituted in first equation and derive the form of x1 can make this equation. x1 is equal to 2 minus x4, like this. Since x2 and x4 remains arbitrary, so we have infinitely many solutions. If we choose a value of x3 and a value of x4, then the corresponding values of x1 and x2 are uniquely determined. For example, it can be noted that if a known remains arbitrary, it is also customary to denote them by other letters T1 and T2 and other letters Tn. This is number of unknowns to be determined. Here is just 2 is enough. In this example, we may thus write x1 is 2 minus x4 equal 2 minus t2. So here we can input t2 to determine the solution. How about here? Just t1. So x2 can be 1 minus t1 plus 4 How about x3? X3 is, as I said before, x3 is just the input number, input variable t1, and x4 is t2. This t1 is first arbitrary unknown, and t2 is second arbitrary unknown. By using these two arbitrary unknown, we can determine x1, x2, x3, and x4 like this. This is the end of example 7.3.3.